Yeah, okay. Because eventually I want to look at this filtration, and I want to tell you some things about it. But before I do that, I'm going to go off on a digression. I want to talk about Verma modules. So remember, my talks are variations on the theme of Frobenius reciprocity, and Verma modules have a kind of Frobenius reciprocity which is really much simpler. So if I take sigma u equals a representation, any finite dimensional representation of P, which is equal to Pk intersect P, then I can define a Verma module, so-called Verma module, as Trappa called it. I don't know exactly what the history of these is. It's very simple. It's a representation of the Lie algebra, U. And so this is just a module. So first of all, it's a module over U of G. It's also a module over K intersect P, and in fact P. I'll explain that in just a moment. So it's what I call a P. So we've seen GK modules, and this is what I might call a GP module. And it has the property that a GK module is one with a lot of K finite stuff, and here it's a representation. So it's a representation simultaneously of the Lie algebra of G and the group P and the sum compatibility condition, and any vector is contained in a p-stable finite subspace. So that's what I mean. So it's the same definition as GK, except that, well, it's P. So almost no representations of the group satisfy this condition. But the representations of the Lie algebra certainly do. Okay, so this is a general, I guess these are called generalized Verma modules. It's a bad name. I call them GP modules. Hello? Yeah, I mean, I'll say something about what the exact structure looks like, but yeah, it's what it is. It's so P, for example, Px on U, right? There's a copy of U sitting here. So we have a P map. So I'm about to state what Frobenius reciprocity is. It's very simple. So this is analogous to the map lambda 1 on the other version. So this is somehow dual to the other inducing representation. So dual to the map from here. So if I look at the induced representation, I have a map from this to U, taking f goes to f of 1, and this is somehow dual in this. I have a P map, a P embedding of U into this just by, there's a copy of P sitting in here by definition of tensor products. And then if I look at any element of G acting on this, and that still generates a p-stable. So this is a union of all these p-stable subspaces, starting with U.
Could you clarify, so
Yeah.
this action of geometry may not lead to action of K itself?
No, the K plays no role in this at all. K intersect P certainly does. Okay. And so K intersect P, for example, acts on this. I think, let's see, it goes like this. It's K X, so I want to have an action of K. Suppose K is a member of K intersect P, then K times X times U. So an element of this tensor product is equal to this, and this is equal to, by definition, it's K X K minus 1 tensor KU. That's the action of the group K intersect P on that, where K X K is the adjoint action of K. Okay? So we have this map. So I have this P map in here, and now there's a general statement. So this is somehow dual. So if I have a G P module V and a G P map from this Verma module from UG cross UP, U to V, then I compose with this, and this gives me a map. So what we have is the following. So let me just tell you what the theorem is, which is Frobenius reciprocity. So the theorem is that GP U of G cross U of P U into V is isomorphic to P, K intersect P from U to V. So it's a kind of a dual Frobenius reciprocity. Oh, because this is the analog of lambda. So, right, I have lambda gives me a map from the induced representation into U, which is a P map. But in this case, I have the opposite. So I have a p-stable copy of U sitting in this thing. So this is dual to my lambda.
Oh, so that the Verma module plays the.
So the Verma module is kind of a dual induced. It's an algebraic version of an induced representation, but it's co-induced, which means everything's dual. Okay. Okay. So this is the version of Frobenius reciprocity. You can see I moved into 12-tone scale here. If I'm playing variations, so it's not quite that bad. It's maybe late 19th century symphony. So we'll call this Frobenius reciprocity. So this Verma construction, oops.
Oh my God.
Oh my God. Oh, I have it, right. Oh, okay, good. I never took it off. Okay. Okay. Any questions? So this is easy to prove. You just generate, it's just some algebraic. It's some basic algebra. Think about tensor products. Yeah.
What is the statement? Any vector is contained in a p-stable subspace. That would be obvious, right?
Well, it's the definition of a GP module. This is a GP module, and
But any vector is always contained in a p by Zorn's lemma.
no, not at all. No, not at all. This is a very strong restriction on the representation. For example, if I look
Any
at
vector is contained in the whole space.
no a p finite means finite dimensional. Oh, I'm sorry, finite dimensional. Right, finite dimensional. Okay, sorry, I said it I think, but didn't write it. Oh, okay. Okay, so this is kind of a formal induced. So this construction is somehow dual. This is an algebraic analog of an induced representation. Okay. Okay. Now,
So the first form starts with a G comma what?
GP, right? Okay, the group PX on this, I remind you of this. So. So this is very, very similar, very analogous to the induced representation construction. Okay, now let's look at this space. So let V equal UG cross UP U. And let's look at its linear dual. So this is a union. So if this is a union of a whole bunch of finite dimensional spaces, on which n acts nilpotently. Remember, I've said that every finite dimensional representation of P is one on which the Lie algebra acts nilpotently. So we'll put it like this. And, well, that's not quite right. It's nki, so some k sub I, because n may not act trivially. I'm not assuming that n acts trivially on that. It's just a finite dimensional representation. So nki times ui equals 0. So each one of those is annihilated by something. Okay. Now, the linear dual, so this is, and these are all finite dimensional subspaces. The linear dual of this is just the linear dual. It's a huge space. It's a projective limit. But here's the thing, and we'll tie this in with this. So V hat is isomorphic to HOM UP K intersect P from UG into U hat. So this is a theorem. It's a trivial theorem. But it's a useful thing. So let me just sort of give it sort of the flavor of this. As I say, this is a union of finite dimensional spaces, and each one of which is annihilated by some power of n. Then in this space, well, so this linear dual is a huge space. The linear dual is the projective limit. So V hat is the projective limit of the UI hats. Right? So this is a direct limit, and then dual to direct limits are projective limits. You don't have to know what a projective limit is, but it's this. I mean, somehow if you know what a projective limit is, then you can sort of see that everything, and in fact, it's a pairing. I'll tell you exactly what the pairing is. So given F, a member of HOM, I'll give you a quote. No, I better not since I'm on tape. Okay. I was going to give you a quote by a famous mathematician of what he thought of this construction, but we'll let it go. Hey, hang on for a minute. And so I want a pairing between this space and this space, and I'll just tell you what the pairing is. So suppose I have a function here. So this function takes something in the developing algebra and is something in the dual here. Now, if I'm given an element of this, I'm given a tensor thing like this, and that's easy. I just take f of x tensor u, and this is a member of u hat tensor u, and then we know there's a canonical pairing of this with this, which goes into C. So that's the map which goes from, so associated to everything here, and I have a map from this into C. So that's what the pairing is. And it turns out it's easy enough to check that this is in fact an isomorphism. Okay?
What's this quote? That's construction.
No, I can't tell you. No. Without telling you who the person is, I'll tell you that when I described this construction to him, he said, "Don't give me any of that horrible algebra." That's what he said. And then later he wrote a paper about it. So, okay. And indeed, so if it looks kind of nasty, well, there's a lot of algebra in here which is somehow not made so explicit in the literature. And this is one of the steps which has never become very popular. But anyway, this is what it is. And now you can see what this is. So this is a dual of this, and this space here, this is a dual of a Verma. So if you ask what is this horrible space here, well, that's easy. It's just a dual of a Verma module. So this space looks pretty nasty, but it's the dual of U tensor G tensor U of P, and I have to just add dual. So that's the dual of this. So that's actually not such a bad space. Yeah.
I don't understand why you call it co-induced.
Because everybody else does.
But there's no reason. It's exactly analogous to.
No, it's co-induced because of the fact that it's precisely because for the induced representation, you have a map from the induced into U, but for the co-induced, you have a map from U into the co-induced. Co means co.
But Frobenius reciprocity, both versions are true, right? If you flip both factors, Frobenius reciprocity is still true.
No.
I mean, if you
It's true for finite groups, but it's not true for anything else. So for finite groups, co-induced and induced are almost the same thing. That's it. That's the only category in which it's true. So for finite groups, it doesn't matter whether you take HOM or whether you take CG, but it gives you the same thing. That's absolutely the only example which holds. But that's because for finite groups, it doesn't matter. For finite groups, if I have a representation embedded in V, then it always splits. So it really is the only finite. Huh?
finite dimensional representations.
Yeah, everything finite for compact groups, but then already you have problems with topology. So, but yeah, that's right. So basically, for compact groups, it's still true if you restrict yourself to finite dimensionals. Okay. For finite groups, you don't even have to do that. It just works out. Okay. Okay, so the whole purpose of my introducing Verma modules here was to show you that the space, so what's really going on here, if I look at dual spaces, so now let's look at the duals of this. So dual to this space, I have maps of topological spaces. I have 0 goes to IW hat, goes to I infinity hat, goes to, and now it's UG tensor UP of U hat. Goes to 0. Actually, there should be a times, well, it's U of the space, but it's sigma times, it's got the delta 1/2 in here, which I forgot. Okay. So it's the same space U, but it's got the action twisted by delta 1/2. So sigma hat times delta, and now it's dual, so it's minus 1/2. Okay. Okay. It's exact, yeah. Yeah, it's everything. These are all very nice topological spaces, so it's for Shea spaces, so you just take the duals.
Say it again. What was the delta 1
It's a signal. I'm just telling you, I'm just reminding you that in this space, this representation, so this is a space U, but the action is sigma times delta 1/2, because that's my definition of induction, right? And that when I take the duals, this is sigma hat. That's the dual of sigma times delta minus 1/2 p, because I've got that delta 1/2 factor. Okay. Now let's actually look at some Verma. So now, let me explain what I'm going to do next in a sort of a general way. I'm looking for maps between principal series. So we've looked for maps between principal series, but actually I can look more generally for maps for things induced. So if I'm looking for maps from one induced representation to another, it just means linear dual in this case, linear dual. So these guys use a star. Yeah, this is one of the places, and we just couldn't agree. So for me, V hat is linear dual. For Trappa, it's V star. I don't know, what does Dragon use? Sure, why not? So for me, here's the really confusing thing. Just so you're totally confused on this question. This is the linear dual, this is the conjugate dual, and this is the K-finite dual. That's what I do. So that's my notation. There you go. I'm sure there's some permutation. We could have 6 lectures, I guess. Yes. Oh, okay. Then.
So your hat is an algebraic dual?
No. Well, my hat is the algebraic dual when it's. If it's an admissible representation, but this is just the algebraic dual, right?
In this case, it's continuous.
But in this case, it's continuous dual.
Continuous. It's not just the linear.
Well, but this is the linear dual is the topological dual if there's no topology. Every space is a direct limit of finite dimensional spaces.
But in this thing that you wrote down, it's exact at some point to take.
These are continuous duals, yes. Right. Right. Okay, now we're interested in investigating. This turns out to be a terribly important thing to do, and even more generally, we've told you, is to understand maps between principal series, GK maps. And as I say, this involves looking at this, so you wind up looking at this thing. So in general, so this leads to investigations of this. So this is the K-finite level. But now it turns out, so this is a fact, and I think it's proven in literature, and it's my theorem, but I didn't prove it in the literature. So that this is the same as this. Maybe I don't think I'll say anything about that again. But anyway, it turns out these are the same spaces. So it turns out that for all practical purposes, if I want to understand this, if I want to understand maps between K-finites, it turns out to be enough to understand. I won't need that technical fact, but there is certainly a map from here to here because I get an embedding from here to here. So if I understand this space, then I pretty well understand this space on general principle, and it turns out actually you understand it completely because they're the same, but that's not needed at any rate. an element, well, at any rate, understanding this space will tell you something about the other space. So, okay, so what I want to understand is this space. So understanding I infinity of sigma divided by nk infinity sigma is important. Well, interesting. My handwriting is truly terrible today. Okay, and it turns out this is finite dimensional. So a fact again, which I'll show in just a moment. So our theorem is that this is finite dimensional. And its dual is there for also finite dimensional.
Totally confused.
Yeah, sure.
There's sigma 1 and sigma 2 there, and there's only a sigma.
Yeah. I mean, this just. So what I'm saying is, there was a lot of verbiage between here and here. So I want to understand this, and that leads to understanding this. And that leads to the general question of understanding this. Okay. Right, I agree. As I was writing it, I felt kind of guilty, so I'm glad you caught me. Okay, so this is so for technical reasons, so we're looking at this, and now we can, but now we're in nice shape because I can look at this. So I have, so the fact that it's finite dimensional is very simple. So what I have is a short exact, so I have this short exact sequence, and now I get from this a long exact sequence, which I won't explicitly mention, but there's certainly I don't know, whatever that thing is. Let me call this I1. Let's call that space I1 infinity. And so this is I1 infinity. I1 infinity. Okay, and so we can show, for example, that this is finite dimensional if we can show that this is finite dimensional and this is finite dimensional. Now, this is finite dimensional because this is the dual of the torsion in a Verma module. That's more or less what I've been saying. So I'm not going to give the details of that, but that's the way this works out. So understanding this space is very simple. It's just the dual of a Verma module, and the torsion in a Verma module is finite dimensional. That's an easy consequence and something I've mentioned already. And so we have to understand this space.
Is the first map in this sequence injective?
No. It usually is. If you remember your homological algebra, there's the next term here is tor 1 un. I just thought I like to sort of upstage you, Matvey, so I've done this. That's the next term in the exact sequence, and tor is not always 0. Okay, but you don't need to know that. That's not an important fact. Well, actually, it is an important fact, but you don't need it now. So what I'll say is, it's tor 1 of blah. Okay. So homologic algebra does give you something that fits into a long exact sequence, but you don't have to know what it is. It's not important because at the moment, all I wanted to convince you of is that this is finite dimensional, and that I just have to know that these things, this is finite dimensional. And now I want to say something about this. Okay. So in one of my previous talks, I introduced the short space of R. So you may think this is a short digression. I have to say, I'm sure that the same thing that I love about representation theory of real groups is probably one of the things that horrifies all of you. You have to know a hell of a lot of stuff from all over anywhere. And this is one of the things that comes out of outer space, but it turns out to be extremely important. So the Schwartz space of R, it's equal to F such that all dk, dxk of F equal to O of 1 over 1 plus absolute value of x, n, all n. So this is functions which are rapidly decreasing along with their derivatives. And now there's a beautiful fact about this, which I think must have been known to almost everybody, but was pointed out by Laurent Schwartz, that this is actually, it's isomorphic to functions on the circle, which vanish at the, well, here's a circle. And so here's R. So we know by stereographic projection that I can make this into R. So I just map stereographic projection, looks like that, and this is infinity. And so if I have a function on R, I can map it onto a function on the complement of infinity, and if it's in the Schwartz space, then that function vanishes of infinite order there. And in fact, every function of infinite order here corresponds to a function of the Schwartz space. So this is kind of an infinity of vanishing of infinite order. At infinity, in fact, so this is in several books of Laurent Schwartz, well, at least 2. But it's just an observation of Laurent Schwartz that works out. And the same thing holds over here. So I have this space IW, and the consequence is, if you sort of pursue this, the consequence is that if, so I have, let's see, let me recall what the situation is. I have a Bruchard decomposition, P omega n intersect P, and now if I assume that my functions behave on the left on this, it's sort of a function is determined by what it restricts to on n and also what it restricts on this, and what happens is that IW restricted to n is isomorphic to the Schwartz space, and n is equal to 1x01, so it's isomorphic to R. And now my IW are things which vanish of infinite are here. If you believe this, you believe that the restriction of IW to n is isomorphic to the Schwartz space. Yeah? Yeah. So ask your question again, I'm sorry.
Could you repeat your argument for IW?
Well, I don't think argument is quite the word. It's a plausibility suggestion. So let me give you my plausibility suggestion. So first of all, let's look at let's argue by analogy or by example. Let's look at the case where I'm just looking at C infinity of P1R. Okay, so that's a simple example of an induced representation. It's sort of a model in many ways for what happens. So in this case, I'm looking, my IW are functions which vanish of infinite order here. Right? Now, this picture is essentially Schwartz's picture. So here we have the projective line. I have infinity. My n orbit is the complement of infinity. And so if I assume that my function vanishes of infinite order here, I get a function in the Schwartz space of R. And in fact, the opposite is true. If I take a function on R and apply stereographic projection, I get a function on the projective line which vanishes of infinite order here. So that's my plausibility argument. Okay. And that works in general. There's some, what you have to do is, in general, what you do is you break up. I know also that G is equal to PWN. Well, I know that the following fact is true, that P, the projective line is a union of 2 copies of the line, and those are n and n orbits. And I take a function, so you look locally somehow and you reduce it to Laurent Schwartz. You can sort of trivialize your bundle in 2 ways and blah, 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 and you get that.
So why is this a proof?
Well, it's almost a proof. Okay, I mean, it goes, you can translate it into a proof, but I'm not claiming I'm giving all the details. Okay.
So just as you get R, you'll get Rn, for example.
If I look at other groups, I'll get other Schwartz spaces, yes. I don't want to say more, I don't think. But yeah, it's always true that if I take, in general, for arbitrary reductive groups, if I take GP, it has a big open orbit. It's equal to G, well, it's equal to P times N bar union sign. Anyway, there's some Bruchard decomposition, and you always get open orbits, and there's some similar statement which applies in general. Yeah, that's right. Okay. Okay. Yeah.
What is the I1 there in the last term in the sequence? I1?
I1 is just the quotient. I just didn't want to keep writing. Have I erased it? Yeah, I've erased it. I just didn't want to keep writing the third term. I had that exact sequence. IW is the, I1 is the Hom, it's the Taylor series at the origin of the principal series.
Right.
Okay. I just didn't want to keep writing I1. Okay.
And what is the dual of the NK torsion?
Well, this is, so we know that I1, and so I1 is the dual
Right.
of a Verma module. And now the Verma module is N torsion. And if you look sort of at the way the duality works, if this is the dual of this, and I look at the dual of this, and then at the N torsion in that, then I get the N torsion in the Verma module. In other words, what I've said is I can recover my I1 as the linear dual of the Verma module. If I want to recover the Verma module from its dual, then I take the N torsion in the dual of this in turn. In other words, there's a double duality, right? I have V goes to V hat, but if I go to V hat hat, it's enormous, because these are all infinite dimensional spaces. So then I look at the N torsion, and then this is this. And that's the way it works. Okay. Okay, so let's see. So let's just see what the immediate consequence is. So I have this space, and as an N space, this is isomorphic to SR modulo, what's X? Well, this is just X by translation. So, yeah, it's a little hard to describe, but anyway, it follows. So because, I'll just say this, yeah, it's a, so NKX by differentiation. So let's see, so this space, as an N space, IW infinity is isomorphic to X. It's the short space of R, and N, remember N is just generated by a single new plus, this X by ddx. Okay, and because it's a vector field on this, and so what I'm looking at is I'm looking at the Schwartz space modulo the image of ddxk times this. So here's a good exercise. This is sort of stupid exercise I really love, I have to confess.
Oh, no, it's not zero because there is some algebraic condition. So it's a finite dimensional space.
It's finite dimensional, so let's actually look at it a little bit. Okay, so here's your calculus question for the day. Let's just take k equals 1 just to get a feel for what happens. Okay, let's think about that. So let's see, what is the image of ddx in SR?
All the functions of the integral is 0.
Yes. So F. Why is that? Why is that?
Which way?
Well,
I mean, if f
this is certainly, so the easy way is from here to here. So if I'm integrating a derivative,
yes.
I get 0, right? If I have a function, the point is this vanishes at infinity, so it's certainly integrable, and if I integrate a derivative, I certainly get 0 again. So that's, and the other way works out all right. I just define, that's right, I'm looking for an f prime of equals to this, so of course I just apply the fundamental theorem of calculus, and so f of x is equal to the interval from minus infinity to x of f of t dt. And because this integral is 0, this vanishes at infinity. That's the important part, and you can check that in fact it vanishes at infinite order. So that's the way that works out. So in general, what's true is I have the, oops, well, I'll state the general fact. So if I have dk dxk, then it's the integral such that integral of x to the L of f of x dx for all L less than k.
So then that's k-dimensional.
And so it's k-dimensional. So the codimension is equal to k. I'm extremely fond of sort of stupid calculus exercises like this. So you get to learn calculus over and over again all your life. Right. Okay. I'm going to stop pretty soon because I'm exhausted, but even though I'm not quite finished. So let me tell you what I'm not going to talk about quite yet. I guess I still have more to do. So let's just discuss things. So we have this space I infinity, and we have this exact sequence that looks like this. And now I want to understand the n torsion invariance, the n and the dual of this thing. That's what you, in order to understand homomorphisms between principal series, that's what I have to understand. And what I can construct very explicitly are n torsion invariants in this and this, and there's some kind of an extension problem. But it turns out that at least if I have an n torsion element here, I can lift it because I have this dual sequence. There's certainly no problem in lifting things that go this way. So what I remember where this discussion started was the following fact. I have, let's look at C infinity of the projective line. Now this has, it contains the constants, and the quotient is equal to a sum of two discrete series, d1 plus d1 minus. And these embed again into the principal series. So in this case, if this is my V, then I have that the dimension of V quotient NV is at least 3 because I have a trivial map into itself, and then these other two things corresponding to maps to the dual principal series emitting to this. And where does that come from? Well, one of them, in some sense, comes from this. I have an integral over this part, so to speak, which gives me something. And then over here, I have a Verma module, and I have, so what must happen is, this is 1, because we know what the dimension here is, it's just 1. So there's only one integral intertwining operator. But what happens over here is there must be some more n torsion sitting in here somewhere, and that's easy to see. What this comes is that I have this a general classification of how Verma modules embed in other Verma modules. And what happens here at the dimension of this case, so what happens to make this all work is the dimension of I1 infinity dual n torsion is equal to 2. And if I were a little less tired, I'd say something about that. I'll leave it here at the moment for that. So I have to talk about a little bit about Verma modules and how they work. I have some very explicit calculations, but I'm just going to stop even though I'm early. Dragan will speak in just a minute.
Sure.
Okay, Dragan will speak at 2 o'clock. Okay, that's all.
Well, we have just 15 minutes.
I know. You can talk for 15 minutes.
I could speak.
No, that's all right. You don't have to do it. Okay. Should we meet? No, okay, we'll just leave it. Are there any questions? This is the n torsion in this space. So this is all. So yeah, actually, I'm sorry. I'm going to speak for another 5 minutes. I'm sorry. I want to. As I say, what I'm interested in doing here is giving you some perspective. So what we have here, what this all leads to, is a discussion of a kind of Verma module.
This sketch proves if you believe the long exact sequence in this Verma module calculation, you've got the n.
Right.
The n code.
Right, so let me tell you where I'm going. That's exactly what I want to do now. So what this leads to is there are two steps. So first of all, suppose that V is a GK, a Harsh-Chandra module. We're interested in classifying maps into principal series, and that leads to classifying spaces that look like this, or it leads to the duals. It leads to this, which is equal to the n torsion in the duals of this. And now, there's no reason, if I look at just one of these for a finite k, for a fixed k, it's slightly ugly space, but now I take the whole sum of these things. So if I start with a Harsh-Chandra module, I look at the n torsion in the dual space, the linear dual. And that's a P. It's a nice GP module. So this gives me a functor associates to every Harsh-Chandra module a GP module. So I think when this was first discovered, and it's just an observation really, it was made by me and I think Kashiwara for some different reasons. you get kind of an association between Harshchandra modules and Verma modules that's not quite obvious, and you may think, and so at first it looks like it's good just for understanding embeddings in the principal series and so on. That's mildly interesting, it's not so important, but what's really important is that it's this space that tells you about the asymptotic behavior of matrix coefficients. And for some reason which I don't quite understand, in order to fully understand the relationship between, fully understand the asymptotic behavior of matrix coefficients, you have to go through this machinery. So for reasons which I'll explain later, so this machinery is required, seems to be required. To understand the asymptotic behavior of matrix coefficients of principal series. Well, or asymptotic behavior of matrix coefficients in general. Again, there are two people in this room who are partly responsible for understanding this, but there's a different way of looking at it along the lines I've been looking at it here. And so the next time I'm still endless talks on principal series. So the next talk on principal series will discuss the asymptotic behavior of the matrix coefficients of principal series, and that will play a role in turn in the Plancherel measure, which Dragan will talk about. So, okay, so that's where I'm going. And in fact, let me say the following. So again, you still may be sort of not convinced that this is an interesting thing. This in turn plays a role in several theorems of Jim Arthur about analogs of the Paley-Wiener theorem. So the matrix coefficient theory plays a role in the Plancherel theorem of Harshchandra's, but it also plays a role in other theorems of analysis, sort of Fourier analysis on the group. Okay. Okay, that's it.